Okay, welcome to the continuation of the morning session. I am delighted to, please hurry to your seats. I am delighted to introduce our next speaker, Amanda Burcroff from Harvard, who will speak on compact hyperbolic Coxeter d-Polytopes with d+4 facets and related dimension bounds.
Thank you. Today I will be telling you about some polytopes that have very nice group theoretic properties called Coxeter polytopes. And the work that I'll be talking on is part of my master's thesis, which was supervised by Pavel Tumarkin. So what is a Coxeter polytope? This is going to be a polytope that lives in Euclidean, spherical, or hyperbolic space, such that all of its dihedral angles, that is, the angles between its facets, are equal to pi over an integer. And so, for example, we have a 30, 60, 90 triangle in Euclidean space, this isosceles triangle in spherical space, and a right-angled pentagon in hyperbolic space. And whenever I draw hyperbolic space, we're going to be working in the disk model. And the study of Coxeter polytopes was popularized by Coxeter when he gave the classification of Euclidean and spherical polytopes in 1934. And currently, these polytopes have some nice applications to the study of minimal volume orbifolds. And for example, you can see the work of Meyerhoff, Kellerhals, or Hild for more on that. And there is a deep connection between Coxeter polytopes and discrete reflection groups, where a discrete reflection group is going to be a discrete group that is generated by taking reflections over hyperplanes in one of our three spaces here. And by hyperplane, I'm always going to mean an affine hyperplane, not a linear hyperplane like we saw in Theo's talk on Tuesday. So if we look at our set of Coxeter polytopes and we want to create a correspondence between discrete reflection groups, well, starting with a polytope, if we take all of the reflections over the facets of the polytope, that will generate a discrete reflection group for us. And in the other direction, if we have a discrete reflection group with bounded domain, and we take that fundamental domain, it will be a Coxeter polytope. So going back to our examples here, if we take our polytopes and we reflect them over their facets, and keep doing this again and again ad infinitum, we will eventually get a tiling of the space. And this tiling has some nice properties. It will cut out all of the hyperplanes that are in the discrete reflection group, and each tile will be your original Coxeter polytope. And as you might expect, these reflection groups are going to be Coxeter groups, where the order of the product of two of the generators is going to be the denominator of the dihedral angle corresponding to the intersection of those two facets. And one way in which we often keep track of the information about how facets intersect in a Coxeter polytope is by looking at a Coxeter diagram. And a Coxeter diagram is going to have a node for each facet of your polytope, and you're going to connect these nodes by lines based on the intersection of those facets. So if that intersection is an angle of pi over 2 up through pi over 5, we connect it with a denominator minus 2 fold edge. And if that denominator is 6 or greater, then we connect those two nodes by an edge whose label is the denominator. And the last case that we'll see most often is if these facets do not intersect, we connect them with a dashed line. And so if we take our polytopes here, and we just are interested in the non-dashed lines here, then we will connect, for example, in our 30, 60, 90 triangle, the two nodes corresponding to the 30-degree angle by an edge with label 6, and a single edge for the angle of degree 60. And so we can take our polytopes and forget the actual information of the polytope and just record these Coxeter diagrams. And so now that we have this language, we can actually say more specifically what Coxeter's classification in spherical and Euclidean space was. So in spherical space, we are going to have the Coxeter polytopes be those whose Coxeter diagrams are unions of these elliptic diagrams. And in Euclidean space, the Coxeter polytopes are going to have Coxeter diagrams that are unions of these parabolic diagrams. And as many of you might notice, these are connected to the finite and affine Dynkin diagrams. But in hyperbolic space, the classification is nowhere near this nice. There's a lot of weird things happening. And so that's why the classification in hyperbolic space is still a very open area of study. And one restriction that I'm going to make before we continue our discussion is that we're only going to be talking about compact hyperbolic Coxeter polytopes. So a polytope in hyperbolic space could have a vertex that lies on the boundary of that hyperbolic space, in which case that vertex is called an ideal vertex. And we're going to be interested only in compact polytopes which have no ideal vertices. Though in the case that you have ideal vertices, you can still end up with polytopes of finite volume, and that's another wide area of study in terms of the classification of these. So let's go into the history of what we do know about compact hyperbolic Coxeter polytopes. Often, when we are studying these, we want to restrict some parameter about these polytopes, because otherwise the space is far too large. And one natural parameter is restricting the dimension. And so it turns out that in dimensions 2 and 3, we have nice classifications of these compact Coxeter polytopes. In particular, in dimension 2, you get essentially all of the polytopes that you could hope for in hyperbolic space. And in dimension 3, we have a nice characterization given by Andreev. But in dimensions 4 and higher, there does not seem to be a nice rule for which polytopes arise. We can also restrict the number of facets of our polytope in terms of the dimension. And there has been some success in studying when the number of facets is close to the dimension of the space. In particular, if the number of facets is the dimension d plus 1, so our polytope is a simplex, these were classified by Lanner in 1950, and they only arise in dimensions 1 through 4. Now, when the number of facets is d plus 2, this classification didn't come until almost 50 years later, given by Kapelinskaya and Esselman, and these arise in dimensions 2 through 5. More recently, we have the classification when the number of facets is d plus 3, given by Pavel Tumarkin in 2007. And these use dimension bounds from Esselman that were given in 1994. The next frontier is the case when the number of facets is the dimension plus 4, which is the case that we'll be focusing in on. And in this case, we know that these polytopes can only arise in dimensions up through 7. This was shown by Anna Felixson and Pavel Tumarkin. And there is a unique polytope in dimension 7. And for the case when the number of facets is 5 or more than the dimension, only sporadic families are known, but there's not really a lot of classification results. And for more information on this very interesting history of hyperbolic polytopes, you can check out Anna Felixson's webpage, where she maintains an updated list of all the progress. All right, so as I mentioned, we're going to be focusing in on this classification when the number of facets is the dimension plus 4. And so far what was known is that there were infinitely many polytopes in dimensions 2 and 3. Those were already classified. And then we have the unique polytope in dimension 7 and none in dimension 7 and higher, which means that we can only get new polytopes in dimensions 4, 5, and 6. And I'm going to be talking about a procedure for getting this classification when the dimension is 4 or 5. And we're going to do so by restricting the space of which polytopes can arise using geometric restrictions, graph-theoretic restrictions, and algebraic restrictions until it's reduced down to a finite problem that is feasible to be checked by a computer. And so starting out with these restrictions, we're going to look at the geometric ones first. So if we take a polytope, we look at its set of normal vectors to its facets, and we apply duality as an oriented matroid we will end up with a set of points that it lies in k-1 dimensional space, where the number of facets was d plus k. And then we can actually normalize these to all lie on the unit sphere. And these set of points are known as the Gale diagram of the polytope. And so in our case, if we are looking at, say, a 4-dimensional polytope with 8 facets, don't try too hard to visualize what that looks like, we are now reducing this down to a 3-dimensional picture, which is a little bit easier to work with. And in this construction, we are luckily still retaining the information of the combinatorial type. That is the information of which sets of facets intersect non-trivially. And this is encoded in the Gale diagram by some condition on the convex hulls of the points. Now, we can actually reduce the dimension of this picture by 1 more by taking a signed projection to a hyperplane. That is a projection where we keep track of which side of the hyperplane these points came from. And through this, we obtain an affine Gale diagram for our polytope, though note that this construction depends highly on which hyperplane you choose. And one thing that we can show is that the affine Gale diagrams of the polytopes that we're interested in are rather limited. They always have a form where they have points in general position with exactly 2 positive points, and these are in the convex hull of the negative points. And so these still record the combinatorial types. So now our goal is to kind of go backwards from these affine Gale diagrams and try and classify what are the possible combinatorial types we could see for these Coxeter polytopes. And to study this, we then look at what is the order type of this point set in the plane, where order type is just the information of which triples of points are arranged clockwise or counterclockwise. And for points up to 11 points, these were classified by Ohrenhammer, Eicholzer, and Krasser in 2002. And so we can use this classification, iterate over all choices of what the positive points could be, and obtain all of the combinatorial types of the polytopes with d plus 4 facets in dimensions 4, 5, and 6. So in dimension 4, this procedure was already completed a little bit differently by Grunbaum and Sridharan. And in dimensions 5 and 6, this is new. And because now we have the classification in dimensions 4 and 5, we can also see that most of these combinatorial types are not actually realized, but are not actually realized by Coxeter polytopes. But this gives us at least a limited list to start with in searching for these Coxeter polytopes. Now, the next set of restrictions that we are going to look at are sort of graph theoretic restrictions, where we return to looking at these Coxeter diagrams that keep track of the dihedral angles. So if we fix a combinatorial type for our polytope, we can then decide what are the set of minimal non-faces, so those facets that intersect trivially, but any subset of them intersects non-trivially. And these are often called missing faces of our polytope. And the subdiagrams of the Coxeter diagrams that can correspond to missing faces were classified by Lanner in 1950, and thus they're called Lanner diagrams. And they're given by this list here. So you'll note that we don't have Lanner diagrams on more than 5 vertices. And in the case that we have 2, 4, or 5 vertices, there's a finite number, and like a small finite number of these Lanner diagrams. And so we can use these restrictions on what certain subdiagrams of our Coxeter diagram can be to start to build up potential Coxeter diagrams for our polytopes. The last set of restrictions that we use to kind of finish up this problem is an algebraic restriction. So for every polytope, we can associate to it a gram matrix where the entries of this matrix are given by the dihedral angles, or determined by the dihedral angles when those facets intersect, and otherwise they are determined by the distance between these facets. And there's a very nice test for telling whether a given matrix is a gram matrix of some polytope. We just need to look at the signature of the matrix, that is, the signs of its eigenvalues. And so we want the signature to be d1 n minus d minus 1, meaning that it has d positive eigenvalues, 1 negative eigenvalue, and the rest are 0. And so because most of the entries of our matrix are going to be determined by the dihedral angles, if we've already, from the previous restrictions, picked out what some of these dihedral angles will be, we can then view the remaining entries as variables in a system of equations given by the rank condition, the fact that this gram matrix needs to have rank d plus 1. So now let me outline the strategy for getting the classification in dimensions 4 and 5. We start out by fixing a combinatorial type, which we got by analyzing the Gale diagrams. We then choose a set of the dihedral angles that are allowed to have an angle of pi over 6 or less, so it can have arbitrarily large denominator. These are sort of the problematic ones to work with, and this set is going to be already very limited by our choice of combinatorial type. We then start to fill in the angles that are pi over 2 through pi over 5 using the restrictions on the Lanner diagrams and just the fact that now the problem is reduced down enough that you can iterate over all such choices. And once you obtain a system that is sufficiently constrained, you can solve using, for example, Mathematica for the remaining entries of the gram matrix using that rank condition. And that will tell you whether or not a polytope with the given set of angles that you've prescribed actually exists. And so using this, we then obtain that there are 348 compact hyperbolic Coxeter polytopes in 4 dimensions with 8 facets, and 51 when we are in dimension 5 that have 9 facets. And I'll mention that this result was also independently found by Ma and Zheng, who gave a different method for the classification, so this adds some certainty that this is indeed the proper list of polytopes. And so rather than have you stare at a list of 399 polytopes, I'm just going to point out a few of the interesting ones. Oh, and also let me mention that in dimension 6, there's no reason that this procedure couldn't potentially be extended to dimension 6. It's just that the amount of data becomes so large that it's no longer feasible for a computer. But it would be very interesting if someone were to complete this classification, though we don't expect to see many new polytopes in dimension 6. But yes, let me point out a few of these polytopes that were particularly interesting. This classification includes the first known polytopes in dimension greater than 3 that have a dihedral angle of less than pi over 10 or equal to exactly pi over 7, as well as the first polytopes in dimension 5 that have a dihedral angle of less than pi over 6. And then one might ask, all right, we've collected all these polytopes, but how is it useful? And one application is in bounding the dimensions of certain families of Coxeter polytopes. So let me just briefly go over the history of what we know about some of these dimension bounds. It was shown in 1984 by Winberg that compact hyperbolic Coxeter polytopes can only arise in dimensions less than 30. And for finite volume polytopes, this is 995. So these are some weird bounds that come out of a very interesting argument. But so far, we only have examples up through dimension 8. And in dimensions 8 and 7, there's only a finite number of examples. And in dimension 6, we do have arbitrarily many examples. And so one way in which we can use this classification is to improve these dimension bounds when the polytope has few facets. So under mild conditions, a face of a Coxeter polytope will itself be a Coxeter polytope. And so we can use this extended classification to give some restrictions on what the structure of these faces can be. And then in the case when you don't really have any nice faces to look at, we also have this other bound on what are called 3 free Coxeter polytopes, so those that only have missing faces of size 2. And combining the cases when we can analyze the Coxeter faces and this bound, we obtain improved bounds on the dimensions of compact Coxeter d-Polytopes with d plus k facets when k is 5 through 10. But as you can see, there's still some gaps between the lower and upper bounds, even in these cases. So this is a nice open problem for people to work on. And there's just so many open problems in this classification that I invite you all to work on. And thank you very much.
Great. Are there questions? Yes.
I was wondering if you could say a bit about what exactly makes the hyperbolic case so much harder than the spherical and Euclidean case. So where do the techniques used for the classification in the spherical and Euclidean case break down in the hyperbolic case?
Start to fail? I mean, in some senses, yes. So the question was, where do the techniques that were used in spherical and Euclidean space break down for hyperbolic space? So why is it the case that this classification is so nice in Euclidean spherical space and not so much in hyperbolic space? I mean, part of the answer is just that's reality, and as we can see, the hyperbolic case is a lot stranger. I mean, I think part of the issue is that in trying to analyze what these elliptic and parabolic subdiagrams are, there's just this nice finite list, or at least like nice finite list of families. Whereas when we're trying to analyze what sorts of subdiagrams can arise in hyperbolic space, we start to get nasty essential subdiagrams. So these are ones that really can't be broken down into other subdiagrams or obtained by like gluing. And so just because there's infinitely many kind of nasty essential examples, this is maybe where this type of classification failed for hyperbolic space.
Other questions? Yes. Oh, you. Oh.
How did you make that picture at the end?
Yeah, that's a great question. So I believe it's Malin Christensen runs a website where if you just Google like reflect hyperbolic pictures or something like this, there's a nice little tool that allows you to input a picture, pick which Coxeter polytope you would like to be your tile, and then creates the tiling for you. So it's a lot of fun to play around with.
Oh, and the question was, how did you make that picture?
Oh, yeah, thank
that
you.
Cool picture. Other questions? Yes, Ben.
I'm kind of curious how you proved your lemma about the Gale diagram, why you can always find the site for that.
So the question was, how did I prove this lemma about the Gale diagram? So why does it have this nice condition that you have like only 2 positive points, and these are in the convex hull of the negative points? And one of the strategies that I used to prove this is sort of one condition that I didn't talk about, which is that to test if a given set of positive and negative points can actually be an affine Gale diagram, there's this condition that if you slice it with a line and you sum up the negative points on one side and the positive points on the other, then this always has to be at least 2 for it to actually be an affine Gale diagram of some polytope. And so it was essentially just using this condition and some argument about being able to slightly perturb the points while maintaining the combinatorial type associated to that affine Gale diagram that allows us to get these diagrams that are in general position and have this nice form.
Okay, thanks. I think maybe we should save other questions for later. You could ask the speaker individually, and the next talk will be at 11:30, so in about 5 minutes. Let's thank the speaker again.